So my name is Upendra and I'm from IPC department at ISC, and I'm going to talk about spectroscopy at molecular junctions, and these are my collaborators, Shaul Mukhalil and Vijay Kumar Agrawala from UCI. He's a postdoc with Shaul there, and this is my student who has worked on these things, just started working on it actually, and I'll talk about some of the results that we have got with him towards the end, if I have time. So this is something that we have recently started working on, and this what I'm going to present is basically a theoretical way to understand these spectroscopic signals at molecular junctions, and of course Latha is an expert in this field, and as Jyotishman said, that there should be no question during the talk. So okay, so what we are looking at is that when there is a molecule attached to two leads, and there is a current flowing through this molecule. So as obviously the molecule is out of equilibrium, as electrons are jumping on the molecule, it creates a kind of polarization in the molecule. It can interact with the molecular vibrations, and that can lead to the nuclear polarizations apart from the electronic polarization. Okay. So how do we understand these polarization and these dynamical effects? Because these can affect the conduction properties of the molecular junction. Of course, spectroscopy is a very good tool to understand these dynamical polarizations in the molecule. And recently, people have started looking at the current conducting pathways inside the molecule. Okay, so different pathways, different bonds inside the molecule can lead to different kinds of conductance, and how to control these conductances or pathways is a new upcoming research field, and where I think the spectroscopy can again help us to understand those pathways. Okay, so this is one experiment which actually motivated us. Here what we see is that these two molecular junctions are, this is done by Rice University group. They analyze these two molecular junctions. Okay, it's fine. So these two molecular junctions they have studied. What they have done here, they have calculated these spontaneous, or they have excited these Raman modes in the molecule, and at the same time they studied the conduction of the molecular junction. What they found is there is a very good correlation between these two signals. One is optical signal, and the other is incoherent charge current signal. Okay. And what they observe is that whenever these modes are excited, they see an enhancement in the conduction of the molecular junction. Okay? Similarly, they have seen the same effect in the other molecular junction. So they call it positively correlated junctions. Okay? Same way, they find some molecular junctions where they're negatively correlated. So if you excite certain modes in the molecule, it suppresses the conductivity of the molecule. Okay? So it tells you that there is a nice correlation between these two responses of the molecule, and if you can control one, you can control the other. Okay, so it leads a way to device manufacture like optoelectronic switches or related devices. So similarly, there is another experiment. Okay, I'll not go into details. They show that these vibrational excitations also show up in the something called ICTS spectrum of the molecular junction, which is the electron, when electron exchanges vibrational energy with the vibration of the molecule, it comes out in the current experiment, current versus voltage experiment, and these excitations are same as you see in the spectroscopy measurements. Okay, the only difference is that here they are very broadened, while these are very sharp peaks. So you can, this gives you better resolution as compared to the simple IV characteristic. Okay, so how do we understand these things? I'm going to discuss something called diagrammatic approach, which is quite standard in spectroscopy. Okay? The only thing we have done here is that we have extended this approach to understand spectroscopy at molecular junctions. As you will see that there are certain differences that you have to be careful in calculating these signals. So what I'm going to discuss is a full quantum formulation, meaning that when you shine light on the molecule and when your signal is coming out, both these modes are treated quantum mechanically. And it has certain advantages because it is symmetric with respect to which mode you're looking at. So semi-classical theory, what did they do? They calculate the polarization induced by the external input light. This polarization they use to solve the Maxwell equations to generate the pulse or the signal. So you treat the incoming mode and the outgoing mode on different footing. Here you can treat everything on the same footing. Okay. And then also the stimulated and spontaneous emission can be treated within the same formulation. And I'll be talking about some Liouville space methods which have some advantages as compared to the Hilbert space method. These are the papers that, so this is the paper where we formulated this method. Here we have applied it, but in the time domain. This is in the frequency domain. And this is the recent work with Himanshu on the electroluminescence. And these are the two works here. This talks about the Liouville space formulation, and I will be using some quantum master equation method, which is described in this work. So I'm going to discuss this experiment where you have three fields. This is the problem with Apple software, this incompatibility between Apple and Windows. So these are the omega 1 and phi 1, omega 2 and phi 2. So these are the different frequencies that my molecule is interacting, and then you have a signal generated in omega 4, and because of the energy conservation and phase matching, these are the phases of the signals, the fields. And this is the phase of the signal, and you can have signal coming out in different phases. Now, in the theory, I will assume that this field is in the coherent state always. Mind that in this case, there is no wave vector matching condition because it's a single molecule experiment. There is no spatial distribution. So there is no phase matching condition, which helps you to actually, in the theoretical formulation, to identify different pathways that lead to the signal. Okay? But the same thing can be done here by phase matching condition instead of wave vector matching condition. Okay? I'll show it to you. Phase matching can select different pathways that contribute to your signal. Okay, this is, again, it's a problem with, I'm sorry, I wish can I change it now, or? No, I have my computer, but I'm sorry. Yeah. I'll do it here quickly. No, wait. Oh, yeah. Let me just do it. There is no backup for this? That one is working. Okay, so I'm going to, sorry for the interruption. I'm going to discuss this particular experiment, and this is the Hamiltonian. Okay, this is not really important. So what we have is signal is calculated perturbatively with the fields. Okay, so I will talk about the third order perturbative calculation, which is called chi3, right? Most common signal. What it has here is, this is my signal, which is coming out at frequency omega 4. It's given by a response of the molecule, which has this structure. Okay, these are the dipole operators of the molecule. So my first pulse, or it can be a CW experiment, laser interacts with it, excites the molecule, creates a polarization. Second one creates another polarization. Third one creates another polarization. And this one is the detection. Okay? So you have 4 interactions here, which are here. You have at tau 1, tau 2, tau 3. These are the times at which interactions taking place. And at time t, I generate the signal. Okay? And these are the Liouville space. This is formulation is done in the Liouville space. So these are the Liouville space operators. They are acting on the density matrix, initial density matrix, and then they excite the molecule, and the density matrix evolves. And then finally you take the trace, which gives you the response function, which appears here. In this case, it's a density matrix of the molecule because I'm treating the field as a perturbative. Okay? So this is the perturbative expansion in terms of the fields. Okay. Now this density matrix, as you said, has leads in it, right? So the lead information is there in the density matrix. Okay. So I'll show you how to treat it, the density matrix, how to calculate it. So this operator is given in terms of left minus right, which is nothing but the operator acting from the left on the density matrix and from the right on the density matrix in the Hilbert space. Okay? So in the Liouville space, all the operators act from the left side, while in Hilbert space, they can act from the left and right. One of the advantages of using Liouville space is that the expressions look very neat. Okay? So the perturbative series is very clear, and all the time orderings, bookkeeping can be very efficient, very clear. Huh? So, yes, so, right. So far I have just done the perturbative expansion with respect to field. So this formula is valid even for the molecule not attached to lead. So it's a general formula for the chi3 signal, okay? So now what happens if I substitute this quantity? So V minus is nothing but the commutator in Hilbert space. If I substitute this operator here, I will generate total 8 terms in this response function. And these 8 terms you can actually express in terms of these so-called loop diagrams. And these loop diagrams, actually you don't need to do all this calculation. If you are familiar with these loop diagrams, you can just write down them intuitively. This is one of the advantages. So what is happening in this loop diagram, what you have to consider is all sorts of interactions possible with your molecule. It's like the Feynman diagram. Okay? So what is happening here is your field comes and interacts with the molecule, it excites it, it can de-excite the next field, stimulate it to ground state, and then excite again and de-excite again. Okay? So now in this case, if you see that if I don't have any lead connected to my molecule, I will generate only 3 diagrams, this, and this diagram. Why is that? Because I can only excite initially my molecule. It's in the ground state, it will never be in the excited state. So only these 3 diagrams are possible. All other diagrams are possible because your system is in non-equilibrium state. Okay? So this we can just write intuitively. This is the power of this theory. Right, so I have not specified is there here because it is in steady state, general state. It can be population or it can be coherent state. I mean, superposition state. Yeah. So initially, if I don't have lead, this interaction is not possible because it will not emit anything. But now it is possible because my system can be in the excited because of electron transfer. Okay, right? Right. So these loop diagrams mean that this time ordering is not taken into account. So these interactions can happen at any time, different times. Now, okay, once I've drawn these diagrams, what can I do with this? Finally, I have to write down the expression for the signal. Okay? So there is a way to read these diagrams. Now, another important thing here is that between these interactions, your system is evolving. Okay? So this evolution in this case is non-unitary because system is interacting with the lead. Okay? But while in the usual case, these are unitary evolutions. So once I have this diagrams, this particular diagram, which is here, the first one, what I can do is that I assume that my system starts from some general state AB, and then it goes and interacts, and then it goes to some other state. And same way, you can label all these states. And so these are the rules to read these diagrams. Time evolution takes place in 3 regions. Here, there is a time evolution, 1, 2, and 3 time evolutions are there. This evolution here evolves this state, which is RB state, to QB state. Okay, and so I can label all these states, and I can calculate these matrix elements. I'll show you how to calculate these matrix elements. So what I have to worry about is this. Once I have labeled these interactions, only thing I have to worry about is the matrix elements of this evolution and the matrix elements of this interaction, which is V. So V will give you matrix element between these 2 states. And also I have to worry about some interactions from the right side, and they will bring another factor of -1 because of this factor here, because it's acting from the right side. Okay? So once I have all these things in place, my signal is nothing but just the product of these quantities. So this is my initial state from which I start with, and then I have matrix elements and the evolutions. For example, this evolution is going from this state EF going to CD, but due to the interactions with previous interactions, so then I have to have all these interactions frequencies into account. So what I do is that, for example, this one, any interaction towards right is negative frequency, any interaction towards left is positive frequency. So this evolution should take place with frequency omega 1 minus omega 2. Same way you can write down this evolution, which should have this frequency argument. Okay? So these are certain rules that you have to keep in mind. Once you are familiar with this, you can immediately write down this expression, and finally you have to sum over all the initial states. Because you don't control those states, these are controlled by the charge transferred from the lead. So you have to sum over all those states. So this, and then this matrix element is nothing but an evolution operator taken between these 2 states, RB to QP. Okay, so these are the inputs to my theoretical expression that I get for the signal. For Hermitian operator, these are diagonal because these states will not evolve to different states if it is unitary evolution. Okay, so it has to be diagonal in these indices. Okay, so once I have done all these things, now next question is how to calculate this quantity. Now remember, this evolution is taking place due to the interaction with the lead also. So there is a Hamiltonian of the molecule and Hamiltonian of the lead, and there is an interaction between these 2. So it's a unitary evolution, non-unitary evolution, and there are different ways to calculate it. 2 most common ways is using something called non-equilibrium gain function, as Bhaskaran said. You can use that, or you can use the master equation approach. So here we will use master equation approach because it is easier, and it takes into account, it's valid when the coupling to the lead is small. This is what we will assume also. Okay? So once I have this, what I can do that, I can write down the master equation using standard ways. I'm not going to show you how to get this, but the density matrix evolves with this equation where L is the so-called Liouvillean or super operator, Liouvillean generally. Yeah, sorry. Oh, this. Okay, so I have associated frequencies. No, with phases. Phases, yes. So you can, I'll show you how to get this thing in phases, but the signal will go in all directions in this case. Okay, it's uniform more or less because there is no wave vector matching condition in this. So yes. I can calculate the density matrix. The simplest way is that, I can calculate so what I need is the density matrix, these operators, these matrix elements and this quantity. And density matrix and this quantity I can get from single equation. I can write down the equation of motion for the density matrix in the basis of the many body states of the molecule. Okay? And using this many body state, I can express this in terms of so once I have this matrix, I can express this evolution operator in terms of the eigenvalues and eigenvectors of this matrix. So once I solve this equation, I get the steady state, I get the evolution operator together. And so I'll skip this part. So same way you can treat the spontaneous signal, but in the spontaneous signal you have a less number of diagrams to calculate. Let me just skip it. Now I'm going to show you the time domain signal, how to calculate. So far I've just shown you the formulation part. So I'm going to apply it now to study the time dependent signal. Okay, nonlinear signal. So molecule is initially prepared in non-equilibrium steady state. It's conducting current, and then I start shining light on it. This is the experiment here. You come up with an initial pulse at with frequency omega 1 at time t1 with phase phi 1. Same way the other interactions happen, and then you have signal generated at omega 4, and it's a heterodyne signal. And that's where the phi is important, because you can change the phi, and heterodyne, you can get the phase information of the signal also. So in this case, because there is a time, now these, yes, in single molecule context, right. So in this case, I actually control these time delays between these signals, and because of this control time delay, my diagrams are not loop diagram, because now the time interactions are fixed. So it's a time order diagram, and I only need to calculate these 8 diagrams in this case, and these diagrams correspond to certain phase matching condition. There will be many more if you are interested in different phase matching conditions. Okay? So in this case, I'm going to apply this, so you can calculate each diagram using the same rules that I discussed earlier. Once I do this, I am going to apply it to a benzene dithiol molecule junction. And in 5 minutes, I can tell you only very few things. Somebody else has done this TDDFT calculation, really. I mean, Charles' group, his postdoc did it, and he found that actually these are the anion and neutral states. Cation states lie very far. Okay? And because of that, and at that temperature we are considering, those states do not populate because of the lead interaction. So there is no charge transfer to those states or from those states. Okay? So we are going to ignore those states. And so using these inputs, and the quantum chemistry calculation can give you the dipole matrix elements also. We use that, solve the quantum master equation to get the density matrix and the evolution operator. Here is just to show you that we can solve this quantum master equation. These are the populations of these anion states, steady state populations, and these are the neutral state population, and these are the coherences between those two states, or those different states in the neutral molecule and in the anion. Okay? And so once we solve this density matrix, what we have to do is to calculate the signal, and here is the result. What I'm doing here is the signal is represented, so I'm going to plot the signal as a function of the time delay between the second and third pulse. Okay? And 2 other time delays are Fourier transformed with frequency omega 1 and omega 3. So what we see here is this: when T2 is 0, when these 2 pulses overlap, okay, there is only diagonal peak in the system. So what these 2 pulses are doing, they are basically creating a population in some state, and these populations show these nice peaks. Okay? And then I vary this T2, and as I start varying this T2, I generate these off-diagonal peaks also. These off-diagonal peaks are actually indicating that there is a population transfer. Once you create in the excited some state, population is transferred to some other state because of the interaction with the lead. So once you create the population, it can decay to some other state because there is exchange with the lead. Okay? So now, so these are the population transfer peaks. So in this case, you see that the main peak is appearing because of these anion states between A prime and D prime here. This is the transition which is coming strongest here. And then small peaks are there because of the neutral molecule. So both the molecule states, neutral and anion states contribute. And in this case, what you see is that the charge transfer is taking place slowly from this anion to a neutral. This peak is because of, these peaks are because of coherences between, charge transfer between the anion and this neutral species. Okay, these peaks are indicative of that charge transfer. Now, I can do another experiment here. Yes. Mixed Hamiltonian, which, yes, so you're right. So here, no. So what I'm saying is that, so this sum here includes all the anion, cation, or neutral, because you don't control it. Right. It can, initially, we thought that we would be able to extract this information, but the optical signal doesn't come out because of transition between different charge states. So then those peaks are missing. You don't have coherences between the charge state and the, at least that information is not there in the signal. Because of, it shouldn't be, but yeah, that's true. But that's what you asked, right? You have to have information about the anion and yes. No, it doesn't. Yeah, it doesn't. So that's why you have signal from the anion and the cation both. Anion and neutral, both. Yes. So it can stimulate the signal from the anion as well as from the cation if it finds proper resonance in both states. Yeah. Okay. So at the same time, what I'm doing is that I'm going to measure the current also. So far I have measured the optical response, but I can measure the current transfer also, like the charge current. Okay. In this case, what I'm going to do, so there are ways to calculate these charge transfer between different sides of the molecule, left side and the right side. And this is the net transfer of the charge in presence of those interactions. And when we plot this, the net charge transfer from the left side and the right side, if you compare it with the optical signal, what you see is that it's nothing but the overlap of these two. If I overlap these two frames, I generate this frame. So what it is telling me is that the charge transfer at the left interface and the right interface has the information about the optical signal. So they are perfectly correlated in that sense. But you have to measure both the charge transfers at the left and the right interface because it is not at steady state anymore. It's a time-resolved experiment. And this is very clear from all these different frames. Okay, so this is one thing that, and then I have 1 minute. Okay. There was interruption also. Okay. Now I'm going to discuss about something electroluminescence, which is nothing but the signal coming out due to the electron and hole transfer recombination. Okay, and these electrons and holes are created not by the external field but by the lead. So electrons can be transferred from the lead and holes can be created by the lead interaction. And then when they recombine inside the molecule, it gives out a spontaneous signal. And this is what we are interested in calculating here. This is the experiment that people have already observed. There are many more, but here they observe this is the molecule, and then electrons come here, and then hole is created at this end, and they claim that the electron hole recombination takes place at this center part. Okay? And this is the signal. In this case, you have only two loop diagrams. Life is much simpler for electroluminescence. Okay? So these two diagrams you can calculate. Yes. Here. Yes. It should, yeah, it can be anywhere, but they claim that this electron, this is a very fast transport of electron through this, but it is blocked in this region. So electron comes here, but it stays here for some time before going here. Yes, and then the electron can go from here to here, creating hole here, and then the recombination basically takes place of this. No, but see, the signal they see is from the center actually. It's not coming out from any other place. I mean, not justifying. I mean, I'm just saying that they claim it. Yeah. So okay. So the same thing it can be done here, but what I have to do here is treat the lead perturbatively. Earlier I didn't treat it perturbatively, but now I have to treat the lead interaction also perturbatively because I want to create electron and hole. If I don't treat it perturbatively, then there can be many electrons created or hole. I don't have control over it. Okay. So once I do this perturbative calculation, well, these are the loop diagrams. These are the time ordered diagrams. The first two interactions create electron and hole in the molecule, and then last two interactions give out the signal. And in this case, you have a signal coming out because of the two resonances. One is the optical resonance. The signal has to have been resonant with the molecular states, and here the bias has to be in resonance with certain states of the molecule. So both these resonances will compete, and we applied it to a molecular junction which I showed earlier. I don't have the same as in the experiment. Okay, so because we did it because we already had data for this. Okay, so we applied it, and the same thing you see here that there are three main peaks in the electroluminescence. And these peaks are coming out mainly because from the anion state of the molecule. So in this case, you don't see any the neutral peak from the neutral molecule. Okay? So, and these peaks intensities nonlinearly increases as you increase the bias. And here is the nonlinear change in the the intensity of the signal as a function of the bias. And these different nonlinear peaks appear because there are two resonances that you have to satisfy, and they can be satisfied at different places in the molecule. In the sense that you can have, because it's a set of many body states, and certain energy difference between certain many body states can be in resonance with the applied bias. And if you change the bias, it may not hit any other resonance until some time when you hit another resonance. So it will show you peak at different energy, different EV applied bias values. Okay. So I'm just going to close this. What we have done is basically taken the standard diagrammatic formulation and extended it to non-equilibrium cases. And as I said, that they can be drawn intuitively, and there are rules to read it. It's a very straightforward calculation. And we applied it for coherent and incoherent optical signals. And finally, we see a nice correlation between charge transfer and the optical signal, which hopefully can be utilized for creating optoelectronic. Thank you.